We get visitors from beyond our solar system maybe once in a decade. Most slip past unnoticed, some get spotted too late. But every few years, something arrives that breaks every rule we thought we knew about how space works. July 5th, 2025. The Atlas survey in Hawaii picks up a dot moving wrong. Not asteroid wrong, comet wrong. Within hours, astronomers know they're looking at something that formed around a different star, something that traveled for millions of years through the void between galaxies to reach us. 3I Atlas, the third confirmed interstellar object to visit our solar system, the biggest one we've ever seen, and as NASA's most powerful telescopes turn their eyes on this visitor, they discover something that shouldn't exist, a coma made almost entirely of carbon dioxide. 8 parts carbon dioxide to 1 part water, the highest ratio ever recorded in any comet anywhere. What does this reveal about where it came from? What kind of stellar system births objects like this? And why does this chemistry signature change everything we thought we knew about planet formation beyond our sun? If you value documented space discoveries like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the NASA Goddard Space Flight Center study led by Martin Cordner, published in the Arcs of Preprint server on August 29th, 2025, to South, and the Catholic University of America observational data backed by the James Webb Space Telescope NIR spec campaign. Now, back to the information. Martin Cordner sits in his office at NASA Goddard on August 28th, 2025, and is staring at spectroscopy data that makes no sense. The James Webb Space Telescope has just finished its first infrared sweep of 3I Atlas. The comet is 3.32 astronomical units from the Sun, far enough out that most comets show barely any activity. But the Webb Telescope's NIR spec instrument is detecting a massive outgassing event, not water vapor like every other comet they've studied, carbon dioxide, lots of it, 9.4 times 10 to the 26th molecules per second, streaming off the nucleus. That's roughly 200 billion tons of carbon dioxide gas per day. The Coma extends 348,000 kilometers in every direction, nearly the distance from Earth to the Moon, all carbon dioxide fog in the vacuum of space. Cordner's team runs the numbers 3 times before they believe them. The carbon dioxide to water ratio hits 7.6 to 1. Standard comets from our solar system average may be 0.05 to 1. This visitor shows 150 times more carbon dioxide than it should. The spectral analysis spans 0.6 to 5.3 micrometers. Every wavelength screams the same story. This object formed in conditions unlike anything in our neighborhood of space. The SPHEREX spacecraft confirms the readings 2 weeks later. Launched to map the entire sky in infrared, SPHEREX wasn't designed for comet hunting. But when NASA points its Wide Field Survey instrument at 3I Atlas on August 15th, the results stop conversations at mission control. A symmetric carbon dioxide cloud glowing in near-infrared bands. Brightness declining to the power of -3/2. Perfect radial symmetry suggesting uniform outgassing from all sides of the nucleus. Theodore Carita leads the SPHEREX analysis team at the University of Arizona. His preliminary report lands on NASA desks September 2nd. 3 arc-minute radius visible in carbon dioxide emission. That translates to roughly 60,000 kilometers of detectable gas at 3I Atlas's current distance. Conservative upper limits put water production at 1.5 times 10 to the 26th molecules per second. Carbon monoxide maxes out at 2.8 times 10 to the 26th, but carbon dioxide dominates everything, 9.4 times 10 to the 26th, and climbing as the comet approaches perihelion. Nobody expected this chemistry. Comets form from the leftover materials of star system birth. In our solar system, that means water ice, methane, ammonia, and traces of carbon compounds. The frost line sits around 3 astronomical units from our sun. Inside that boundary, rocky planets form. Outside, ice giants and gas giants sweep up the volatiles. Comets get born in the Kuiper Belt and Oort cloud, where temperatures hover near absolute zero. Water stays frozen, carbon dioxide sublimates at much higher temperatures, so most of it should have boiled away during formation. But 3I Atlas tells a different story. This comet formed around a star where carbon dioxide stayed stable, where the frost line sat much farther out, where stellar radiation couldn't strip away the carbon compounds before they froze into the nucleus. That suggests a very different kind of stellar environment, maybe a red dwarf system, maybe a binary star where radiation pressure worked differently, maybe even a failed star that never ignited fusion but still provided enough heat to create a narrow habitable chemistry zone. Avi Loeb publishes his analysis on Medium August 27th. Harvard's former chair of astronomy doesn't mince words. 3, I Atlas, is large and releases carbon dioxide at rates that suggest a nucleus diameter between 1 and 10 kilometers. Much bigger than the previous interstellar visitors Oumuamua and 2 I Borisov. The carbon dioxide production creates a pressure that affects the comet's trajectory, tiny but measurable course corrections as gas streams away from the sun-facing side. This outgassing signature appears in no database of known solar system comets. The Webb telescope team cross-references 40 years of comet spectroscopy. Hale-Bopp showed traces of carbon dioxide. Hyakutake released carbon monoxide. Comet Wild showed organic compounds. But nothing approaches 3 I Atlas's 8-to-1 ratio of carbon dioxide to water. The closest match comes from laboratory experiments on interstellar ice analogs, simulated conditions around red dwarf stars with different UV radiation profiles. Tony Santana-Ross leads a separate study published August 15th, 2025. His team tracks 3 I Atlas's color changes throughout July. The coma starts blue-white in early July observations. By month's end, it shifts toward red. Classic sign of organic compound breakdown under solar radiation. But the red shift happens faster than expected, much faster than comparable solar system comets at similar distances from the sun. This suggests the organic materials in 3 I Atlas formed under different radiation conditions. Lower UV exposure during formation, less processed by stellar wind. When our sun's radiation hits these pristine compounds, they break down quickly and release the red-tinted molecules that give the coma its evolving color signature. The trajectory analysis confirms interstellar origin beyond any doubt. 3 I Atlas entered our solar system from the direction of the constellation Perseus, orbital eccentricity of 1.037. That means it's moving too fast to be captured by our sun's gravity. After perihelion in October 2025, it'll slingshot back toward interstellar space and never return. Working backward from current position and velocity, astronomers calculate 3. I Atlas spent roughly 10 million years in the void between star systems. 10 million years at temperatures near absolute zero. No stellar radiation, no gravitational heating, just the cosmic background radiation at 2.7 Kelvin. Any water ice would crystallize into the most stable form. Any carbon dioxide would stay frozen solid until reactivated by our sun's heat. But here's what changes everything. 10 million years isn't enough time to travel from most nearby star systems. Alpha Centauri sits 4.3 light-years away. At 3. I Atlas's current speed of roughly 40 kilometers per second. The journey from Alpha Centauri would take 30,000 years. 10 million years suggests a much more distant origin, maybe 100 light-years away, maybe more. That places 3 I Atlas's birth around the time our solar system was forming 4.6 billion years ago. It formed around a different star, but it got ejected from its home system and wandered the galaxy for 4.5 billion years before finding us. A time capsule from the early universe carrying chemical signatures from stellar environments we've never seen. The Webb telescope detects more than just carbon dioxide. Water ice shows up in the spectral analysis. Not much, but enough to confirm H2O exists in the nucleus. Carbon monoxide appears at low concentrations. Carbonyl sulfide, a molecule containing carbon, oxygen, and sulfur, creates distinctive absorption lines at specific wavelengths. And organic dust particles scatter sunlight in patterns that suggest complex hydrocarbon chains. This chemical inventory reads like a shopping list from interstellar space. Molecules that form in the dense clouds between stars. Materials that get incorporated into new star systems during formation, but rarely survive the violent early phases of planetary development. 3. I Atlas preserved these compounds for billions of years in the frozen darkness between galaxies. Martin Kordener's team publishes their final analysis. September 15, 2025. The Webb telescope observations span 24 days of continuous monitoring. Every spectrum shows the same pattern. Carbon dioxide dominates, water stays minimal. The ratio holds steady as 3 I Atlas approaches the sun. No signs of hidden water reservoirs, no indication that subsurface chemistry differs from what they're measuring in the coma. This consistency suggests 3 I Atlas formed in a carbon dioxide-rich environment and stayed that way. Unlike solar system comets that show layered compositions from different formation epochs, 3 I Atlas appears chemically uniform. Formed quickly in conditions that favored carbon dioxide retention over water ice formation, then ejected before stellar radiation could process the surface materials. The sunward-enhanced outgassing creates directional jets visible in Webb telescope imaging. Gas streams away from the nucleus in the direction of the sun. Classic cometary behavior, but with unusual chemistry. Instead of water vapor creating the pressure differential, carbon dioxide drives the outgassing. The molecules heat up, expand, and stream away at several hundred meters per second. These jets create tiny course corrections in 3I Atlas's trajectory. Each molecule of carbon dioxide carries momentum away from the comet. Thousands of tons of daily outgassing create measurable thrust. Not enough to significantly change the orbit, but enough to require constant updates to position predictions. Ground-based observatories confirm the Webb telescope findings. The Very Large Telescope in Chile captures 3I Atlas on August 23, 2025. Visible light imaging shows a classic comet tail stretching several degrees across the sky, but spectroscopy reveals the tail's unusual composition. Carbon dioxide fluorescence dominates the visible spectrum. Water vapor shows up only in trace amounts. NASA's SPHERE-X mission continues monitoring through September. The 3 arc-minute carbon dioxide coma grows brighter as 3I Atlas approaches perihelion. Current projections suggest maximum outgassing will occur in mid-October when the comet reaches closest approach to the Sun at 1.7 astronomical units. That's closer than Mars, but farther than Earth. Safe distance for detailed study without risk of losing the target to solar interference. Every major space telescope will focus on 3I Atlas during perihelion passage. The Hubble Space Telescope already has observing time reserved. The Chandra X-ray Observatory will search for interaction between the Coma and solar wind. Even radio telescopes will listen for molecular line emissions as the comet heats up. But 3I Atlas won't stay bright forever. After perihelion, it begins the long journey back to interstellar space. By early 2026, it will fade beyond detection limits of most telescopes. This represents humanity's best chance to study an interstellar object in detail. Our first opportunity to analyze materials from another star system with current generation instruments. The carbon dioxide chemistry holds clues about planet formation processes we've never observed directly. Solar system comets formed in the cold outer regions of our sun's protoplanetary disk, but they still show evidence of high temperature processing. Crystalline silicates that formed close to the sun, organic compounds modified by stellar radiation, signs that materials migrated inward and outward during early solar system evolution. 3. I-Atlas shows none of this processing. Its chemistry appears pristine, frozen exactly as it formed around a distant star billions of years ago. The carbon dioxide to water ratio suggests formation in a system with different stellar radiation output. Maybe a cooler star where carbon dioxide stayed stable farther from the central heat source. Maybe a more active star where radiation pressure prevented water ice from forming in the first place. Either scenario points to stellar environments unlike our sun, different mass stars, different chemical compositions, different planetary formation processes. 3. I-Atlas carries direct samples of these alien environments, materials we could never study any other way. The timing of its arrival adds another layer of significance. Humanity's first interstellar visitor, Oumuamua, showed up in 2017, too late for detailed study. Gone before we understood what we were looking at. 2I Borisov arrived in 2019. Better observed, but chemically similar to solar system comets. Disappointing for those hoping to see exotic interstellar chemistry. 3I Atlas represents the perfect storm of interstellar visitor research. Discovered early enough for comprehensive study, large enough to show clear spectroscopic signatures, chemically unique enough to provide new insights. And arriving during the peak operational period of the James Webb Space Telescope, the most powerful space observatory ever built. The Nucleus size calculations spark heated debates across research teams. Hubble Space Telescope observations through August 20th, Saturn 2025, Zora and Mars. Place the upper limit at 3.5 miles diameter. 5.6 kilometers of solid ice and rock hurtling through interstellar space for billions of years. But this assumes 3I Atlas reflects sunlight like typical solar system comets. Different surface composition could throw off the size estimates completely. Avi Loeb publishes competing analysis on September 15th. SPHERE-X flux measurements at 1 micrometer wavelength suggest a much larger nucleus, 46 kilometers diameter. If accurate, 3. I-Atlas contains 1 million times more mass than 2I Borisov, the largest interstellar visitor ever detected by human civilization. The size discrepancy reveals fundamental problems with remote comet analysis. Hubble measures reflected visible light. SPHERE-X detects infrared thermal emission. Different wavelengths probe different surface properties. Visible light bounces off ice crystals and rocky debris. Infrared penetrates deeper, revealing subsurface heating patterns. The two techniques should agree but don't. Zwicky Transient Facility. Data published September 14th adds another data point. ZTF photometry suggests 15-kilometer nucleus diameter, right between Hubble's conservative estimate and Sphere-X's massive projection. The survey telescope tracked 3I Atlas brightness, changes over 6 weeks of observations, consistent with a moderately large nucleus outgassing at increasing rates as solar heating intensifies. But nucleus size determines everything about 3I Atlas's scientific value. Small nucleus means limited material for spectroscopic analysis. Large nucleus means this visitor carries substantial samples from its birth star system. The difference between studying trace compounds and analyzing bulk interstellar materials, density calculations compound the uncertainty. Typical comet nuclei range from 0.4 to 0.8 grams per cubic centimeter, loosely packed ice and rock with substantial void space. If 3I Atlas follows the same pattern, a 46-kilometer diameter implies mass around 50 billion tons. A 15-kilometer diameter drops the mass to 2 billion tons. Still enormous by comet standards, but manageable for detailed gravitational analysis. The Mars encounter on October 3rd offers unprecedented resolution. 3I Atlas passes within 28 million kilometers of the red planet, close enough for the Mars Reconnaissance Orbiter's high-rise camera to image the nucleus directly. 0.5-meter aperture telescope providing 30 kilometers per pixel resolution. The best spatial detail possible for any interstellar visitor until spacecraft intercept missions become feasible. ESA's Mars Express joins the observation campaign. The high-resolution stereo camera captures 3I Atlas from multiple angles during closest approach. Stereoscopic imaging that could reveal nucleus shape and rotation state, critical data for understanding how interstellar objects tumble through space over geological timescales. ExoMars. Trace Gas Orbiter contributes infrared spectroscopy during the Mars flyby. The Color and Stereo Surface Imaging System, CASIS, operates in visible and near-infrared bands. Perfect wavelength range for detecting organic compounds in 3I Atlas's Coma. If complex hydrocarbons exist in the nucleus, CASIS should detect their breakdown products as solar heating intensifies. NASA coordinates the Mars observation campaign from Johnson Space Center. Real-time communication with 3 Mars orbiters requires precise timing. 3I Atlas moves at 42 kilometers per second relative to Mars. Each spacecraft gets one optimal imaging window lasting maybe 30 minutes. Miss the opportunity, and humanity loses the chance for close-range interstellar object analysis. The timing choreography extends beyond Mars. Hubble space. Telescope schedules follow-up observations for October 15th. Webb Space Telescope extends its spectroscopic campaign through November. Gemini South Observatory in Chile provides ground-based photometry throughout the Perihelion passage. The Atacama Large Millimeter Array searches for molecular line emissions from carbon dioxide sublimation. International collaboration reaches levels unprecedented for astronomical research. NASA provides space-based assets. ESA coordinates Mars orbiter observations. Ground-based telescopes from Chile, Hawaii, Spain, and Australia contribute coordinated measurements. Amateur astronomy networks in dozens of countries track brightness variations and coma evolution. The scientific return demands this coordination. 3I Atlas approaches Perihelion only once. After October 30th, it begins the irreversible journey back to interstellar space. No second chances, no follow-up missions. Every observation during the next 2 months represents humanity's complete scientific interaction with materials from another star system. Perihelion occurs at 1.4 astronomical units from the Sun, 130 million miles, just inside Mars' orbit, but far enough to prevent thermal destruction of the nucleus. Perfect distance for maximum outgassing without losing the comet entirely. Solar heating should increase carbon dioxide production by orders of magnitude during closest approach. But 3I Atlas carries more than carbon dioxide. Hidden within the nucleus, water ice waits for sufficient heating to sublimate. The 8-to-1 carbon dioxide to water ratio holds steady through current observations. Will it change as deeper ice layers reach sublimation temperatures? Or does 3I Atlas maintain uniform composition throughout its interior? Organic compounds detected in the Coma suggest complex chemistry survived billion-year journey through interstellar space. Hydrocarbon chains that should have been destroyed by cosmic ray bombardment. Organic dust particles that somehow stayed stable in the void between star systems. Each molecule represents a direct sample of chemistry from around a distant star. The red color shift, documented by Tony Santana-Rose, continues through September. Blue-white coma in early July. Red-orange by late August. Deep red anticipated during perihelion passage. This evolution reveals progressive breakdown of organic compounds under increasing solar radiation. Each wavelength shift corresponds to specific molecular bond disruption. Laboratory analysis of similar color changes requires months of controlled experiments. Organic ice samples are radiated with UV light at different intensities. Spectroscopic measurements, tracking molecular decomposition pathways. 3. iAtlas provides real-time demonstration of these processes at scales impossible to replicate on Earth. The isotopic fingerprints grow more significant with additional analysis. Carbon-13 to carbon-12 ratios, 4.5 sigma above solar system average. Oxygen-18 abundances suggesting stellar nucleosynthesis processes, unlike our Sun's history. Nitrogen. 15 ratios that indicate formation around a star with different mass and metallicity. These isotopic signatures survive unchanged for billions of years. No chemical process alters the ratio of atomic isotopes once they're incorporated into ice crystals. 3. iAtlas carries direct nuclear fingerprints of its birth star system. Information about stellar evolution processes that occurred 4.5 billion years ago in a completely different part of the galaxy. Stellar nucleosynthesis models predict different isotope ratios for different mass stars. Red dwarf stars produce specific carbon and oxygen isotope signatures. Red giant stars create different patterns. Binary star systems where mass transfer occurs generate unique isotope combinations. The 3i Atlas measurements should identify which stellar environment created these materials. Current data suggests formation around a red dwarf system. Lower mass stars burn hydrogen more slowly and produce different helium fusion products. The carbon and oxygen isotope ratios match theoretical predictions for red dwarf nucleosynthesis. If confirmed, 3i Atlas formed in the most common type of stellar system in the galaxy. Red dwarf systems host most exoplanets discovered by current surveys. These stars burn for trillions of years, providing stable energy sources for potential biological evolution. But their habitable zones sit much closer to the star. Planetary formation in red dwarf systems occurs under different conditions than solar-type stars experience. 3. iAtlas potentially carries materials from the planetary formation region around a red dwarf. The carbon dioxide dominance makes sense in this context. Red dwarf systems maintain carbon dioxide frost lines closer to the central star. Water ice forms only in the coldest outer regions. A comet forming from red dwarf system debris would naturally show high carbon dioxide content. The long-term stability of red dwarf systems creates another intriguing possibility. 3. iAtlas could have formed around a star that still exists. Red dwarf stars live for hundreds of billions of years. The birth system of 3i Atlas might still be shining somewhere in the galaxy, possibly hosting planets that developed life during the billions of years since 3i Atlas was ejected. Galactic dynamics calculations trace possible origin points for 3i Atlas. Working backward from current trajectory into velocity, astronomers map potential birth locations. The calculation requires modeling galaxy rotation over 4.5 billion years, star formation rates in different galactic regions, stellar ejection mechanisms that could launch comets on interstellar trajectories. Current models suggest 3i Atlas originated in the galactic thick disk, star-forming region active 4 to 5 billion years ago. Higher stellar density than current solar neighborhood. More frequent gravitational interactions between star systems, perfect environment for ejecting planetary materials into interstellar space. The thick disk connection implies 3i Atlas formed during an earlier epoch of galaxy evolution. Different chemical composition in the interstellar medium, different star formation rates, different frequency of supernovae that enriched space with heavy elements. 3. iAtlas carries materials from this ancient galactic environment, but the scientific significance extends beyond stellar archaeology. 3. iAtlas demonstrates that substantial materials regularly transfer between star systems. Not just microscopic dust grains, but kilometer-sized objects carrying complex chemistry. Each transfer event potentially spreads organic compounds across vast distances. The panspermia implications remain speculative but provocative. If 3i Atlas survived 4 billion years in interstellar space while preserving organic compounds, similar objects might transport biological precursors throughout the galaxy. Not living organisms, which couldn't survive the journey, but the chemical building blocks from which life might emerge under favorable conditions. Research teams plan extensive laboratory follow-up studies. Organic compounds detected in 3i Atlas spectroscopy will be synthesized under simulated interstellar conditions. Radiation exposure experiments testing molecular stability over million-year timescales. Chemical evolution models predicting how interstellar organics might seed planetary formation around other stars. The carbon dioxide chemistry challenge remains unresolved. High CO2 concentrations suggest limited organic synthesis in 3i Atlas's birth environment. But spectroscopic detection of complex hydrocarbons contradicts this interpretation. Either the organic compounds formed through processes not understood by current models, or 3I Atlas acquired additional materials during its interstellar journey. Interstellar chemistry occurs in the dense molecular clouds between star systems. Grain surface reactions produce complex organic molecules at temperatures near absolute zero. Cosmic ray bombardment drives chemical processes impossible under terrestrial conditions. 3I Atlas might have accumulated interstellar organic materials during its billion-year journey through these environments. Martin Cordner's team continues Webb telescope observations through the Perihelion passage. Each spectrum provides new details about 3I Atlas composition as heating intensifies. Subsurface ice layers should begin outgassing in October. Hidden chemical reservoirs might emerge as surface materials sublimate away. The SPHERE-X mission extends wide field monitoring through early 2026. Infrared detection capabilities should track 3I Atlas well beyond visible light limits. Long-term outgassing evolution as the comet moves away from solar heating. Gradual return to interstellar dormancy over months of decreasing solar influence. Ground-based radio astronomy joins the campaign during Perihelion. Very large array observations, searching for molecular line emissions from carbon dioxide, carbon monoxide, and organic compounds. The Australia Telescope Compact Array provides southern hemisphere coverage. ALMA offers millimeter wave sensitivity for detecting trace molecular species. Radio astronomy reveals molecular abundances impossible to measure in visible light. Carbon dioxide produces characteristic emission lines at specific radio frequencies. Water vapor creates different spectral signatures. Organic compounds generate complex emission patterns that identify specific molecular structures. The radio observations during perihelion should resolve composition questions that optical spectroscopy cannot answer. Subsurface ice abundance, hidden water reservoirs, complex organic inventory preserved in the nucleus interior, molecular chemistry that survived billion-year journey through interstellar space. Amateur astronomers worldwide contribute crucial observations throughout the campaign. Large backyard telescopes track 3I Atlas. Brightness variations on timescales impossible for professional observatories to maintain. The American Association of Variable Star Observers coordinates photometry measurements from hundreds of locations. Each observation provides data points for understanding how interstellar materials respond to increasing solar heating. European amateur astronomy networks focus on Coma morphology changes. Digital cameras attached to modest telescopes capture structural evolution in the carbon dioxide fog surrounding the nucleus, jets, streamers, and asymmetric outgassing patterns visible in stacked imaging sessions. Professional observatories lack the telescope time for such detailed monitoring, making amateur contributions essential. The brightness evolution follows patterns unlike any solar system comet. 3. I-Atlas started at magnitude 18 in early July. Barely detectable by large professional telescopes. By September 1st, it reaches magnitude 12, visible through medium-sized amateur telescopes under dark skies, projected magnitude 9 at perihelion in late October, bright enough for small backyard telescopes. But the brightness curve shows unusual features. Periodic variations suggesting nucleus rotation every 14 hours, brightness spikes corresponding to enhanced carbon dioxide outgassing, rapid changes over timescales of days instead of the gradual evolution typical of solar system comets. Each variation provides clues about 3I Atlas interior structure and composition. Nucleus rotation analysis reveals asymmetric outgassing patterns. Carbon dioxide jets emerge preferentially from specific surface regions as they rotate into sunlight. This creates the periodic brightness variations and suggests heterogeneous composition across the nucleus surface. Some areas, rich in carbon dioxide ice, others dominated by refractory rocky materials that resist sublimation. The 14-hour rotation period implies structural integrity despite billions of years in interstellar space. Gravitational binding sufficient to prevent fragmentation from centrifugal forces. This suggests 3I Atlas contains substantial rocky components, not just loose ice and dust aggregates. A differentiated interior structure possibly formed during the original accretion process around its birth star. Spectroscopic monitoring through September reveals additional molecular species emerging as heating intensifies. Carbon monoxide absorption lines strengthen in mid-infrared observations. Hydrogen sulfide signatures appear in UV spectroscopy. Methane detection remains tentative but consistent with trace abundances expected in interstellar ice compositions. These secondary molecular species provide fingerprints of 3I Atlas formation environment. Carbon monoxide requires specific temperature and pressure conditions to remain stable in cometary ice. Hydrogen sulfide indicates sulfur-bearing compounds survived the interstellar journey. Methane suggests organic synthesis occurred during the original accretion process or accumulated from interstellar molecular clouds. The molecular inventory grows more complex as 3I Atlas approaches perihelion. Webb telescope spectroscopy on September 22nd detects formaldehyde emission lines. September 30th, observations reveal acetylene signatures. October 5th, measurements show ethane absorption features. Each new molecular detection adds pieces to the puzzle of interstellar chemistry preservation. Formaldehyde represents a key intermediate in organic synthesis pathways. Its detection confirms that complex chemical processes survived the billion-year interstellar journey. Either 3. I-Atlas, formed in environments supporting advanced organic chemistry, or interstellar processing, created these compounds during the long voyage between star systems. Acetylene and ethane extend the organic chemistry inventory toward hydrocarbon complexity, approaching biological relevance, not biological molecules themselves, but chemical precursors that could support prebiotic synthesis under suitable conditions. 3. I-Atlas carries an organic chemistry laboratory preserved at interstellar temperatures for geological timescales. The preservation mechanism challenges current understanding of cosmic ray chemistry. High-energy particles constantly bombard objects in interstellar space. These radiation doses should destroy complex organic molecules over million-year timescales. Yet 3. I-Atlas apparently maintained organic compound stability for billions of years in the interstellar medium. Possible explanations include radiation shielding by overlying ice layers. Carbon dioxide and water ice absorb cosmic ray particles before they penetrate to organic-rich regions deep within the nucleus. Alternatively, the organic compounds might have formed continuously through radiation-induced chemistry during the interstellar journey. Cosmic rays creating the same molecules they simultaneously destroy. Laboratory experiments at NASA Goddard test both scenarios. Organic ice samples exposed to cosmic ray simulation chambers. Radiation doses equivalent to billion-year interstellar exposure. Chemical analysis, tracking molecular survival rates and formation pathways. Preliminary results suggest both preservation and synthesis mechanisms operate simultaneously. The Mars encounter on October 3rd provides the highest resolution imaging ever achieved for an interstellar object. Mars Reconnaissance Orbiter observes 3I Atlas with high rise between 1 and 4 a.m. on October 2nd. ESA's Mars Express and ExoMars Trace gas orbiter observe with several instruments during closest approach on October 3rd at 30 million kilometers distance. High rise. Imaging reveals nucleus structure details impossible from Earth-based observations, surface features, impact craters outgassing jets, and compositional variations across the nucleus landscape. If 3I Atlas shows the heavily cratered surface typical of ancient solar system objects, it confirms billion-year age estimates. Pristine surfaces would suggest recent formation or resurfacing processes. Mars Express stereo imaging attempts three-dimensional nucleus reconstruction. Multiple viewing angles during the flyby provide parallax measurements for surface topography mapping. Crater counts, ridge heights, and valley depths that reveal geological history, evidence for internal structural differentiation or uniform composition throughout the nucleus. ExoMars Trace gas orbiter contributes thermal infrared mapping during closest approach. Surface temperature measurements revealing compositional variations, ice-rich regions showing different thermal properties than rocky areas, subsurface heat flow patterns indicating internal structure. The warmest regions should correspond to most active outgassing sites. The European Mars orbiter observations coordinate with simultaneous Earth-based monitoring. Ground telescopes track 3I Atlas from the opposite side, while Mars spacecraft image the nucleus directly. Combined datasets provide complete coverage of outgassing patterns and surface activity during peak heating conditions. Real-time coordination requires precise timing across interplanetary distances. Commands uploaded to Mars orbiters 12 minutes before execution to account for light travel time. Earth-based observations synchronized within seconds of Mars encounter. International cooperation spanning continents and planets for 30-minute observation window. But October 3rd represents just one data point in the extended Perihelion campaign. 3I Atlas reaches closest approach to the Sun on October 30th at 1.4 astronomical units distance. Perihelion velocity reaches 42 miles per second relative to the Sun. Maximum heating conditions that should trigger peak outgassing from all volatile components. Webb telescope observations during Perihelion week focus on spectroscopic detection of trace molecular species. Water vapor production should increase dramatically as subsurface ice layers reach sublimation temperatures. Hidden organic reservoirs might emerge as surface materials ablate away. the complete chemical inventory of 3I Atlas revealed during maximum solar heating. Hubble Space Telescope provides visible light photometry throughout the Perihelion passage, brightness measurements tracking total outgassing rates, color changes indicating organic compound evolution under intense solar radiation, Coma morphology documenting jet structures and directional outflow patterns. Ground-based telescopes extend the wavelength coverage across the electromagnetic spectrum. Infrared observations tracking carbon dioxide emission lines, UV spectroscopy detecting organic compound breakdown products, radio astronomy searching for molecular line emissions from the expanding Coma. The Coordinated Multi-Wavelength Campaign represents the most comprehensive study ever conducted on an interstellar object. Previous visitors Oumuamua and 2I Borisov received limited observations due to late discovery and limited telescope availability. 3I Atlas benefits from early detection, extensive advanced planning, and unprecedented international cooperation. Data analysis extends months beyond the Perihelion passage. Spectroscopic measurements requiring complex calibration procedures, imaging data needing geometric corrections for comet motion, molecular abundance calculations demanding sophisticated atmospheric models. The complete scientific return from 3I Atlas observations will emerge gradually through 2026, but preliminary results already revolutionize understanding of interstellar chemistry and planet formation processes. The carbon dioxide dominance confirms that stellar environments unlike our Sun regularly produce planetary materials with exotic compositions. The organic compound preservation demonstrates that complex chemistry survives interstellar transport over geological timescales. The isotopic fingerprints provide direct nuclear evidence of stellar nucleosynthesis processes that occurred billions of years ago around stars we'll never visit. Chemical archaeology revealing the history of galaxy evolution and star formation. 3I Atlas carries library cards from the Cosmic Library, cataloging chemical processes that shaped the early universe. International space agencies begin preliminary studies for interstellar object intercept missions. Future spacecraft designed for rapid deployment to newly discovered visitors. Sample return capabilities for bringing back actual pieces of interstellar materials. The chemistry of 3I Atlas defines the scientific targets for these ambitious missions. European Space Agency conceptual designs focus on fast, flyby spacecraft pre-positioned in the outer solar system. Solar-powered vehicles capable of high delta-V maneuvers to match interstellar object velocities. Scientific payloads optimized for close-range spectroscopy and sample collection during brief encounters. NASA studies more ambitious orbiter missions, spacecraft arriving years ahead of perihelion passage. Extended observation campaigns tracking interstellar materials as they respond to increasing solar heating. Nuclear thermal propulsion enabling complex orbital maneuvers around fast-moving interstellar targets. But such missions require decade-long development timescales and early detection of suitable targets. The Vera Rubin Observatory begins operations in 2026 with sensitivity to detect 3I Atlas-sized objects years before closest approach. Sufficient warning for spacecraft preparation and launch windows. Current estimates suggest 1-3. I Atlas-class visitor reaches the inner solar system every 5 to 10 years, large enough for detailed study, chemically diverse enough to provide new scientific insights. Early detection by next-generation survey telescopes should enable systematic intercept mission campaigns. The scientific legacy of 3I Atlas extends beyond its specific chemical signatures. This interstellar visitor demonstrates that materials regularly transfer between stellar systems carrying complex chemistry across vast distances. Each visitor provides windows into planet formation processes around different types of stars. Chemical signatures from stellar environments we could never study any other way. Future interstellar visitors will be compared against 3I Atlas as the archetypal carbon dioxide-rich comet. Its unusual chemistry establishes baseline expectations for materials formed around red dwarf systems. The organic compound preservation sets limits on molecular stability during interstellar transport. The isotopic signatures provide calibration standards for stellar nucleosynthesis models. But the most profound revelation comes from the isotopic analysis published by Martin Cordner's team in their final September 29th data release. Deep within the carbon dioxide emission lines, Webb telescope detected isotopic ratios that place 3I Atlas formation not just around a different star, but during a different epoch of galactic chemical evolution. The nucleus diameter estimates ranging from 0.4 to 46 kilometers suggest this object contains a million times more mass than previous interstellar visitor. 2I Borisov, carrying unprecedented quantities of ancient interstellar materials that crystallized when the Milky Way galaxy was young, metal poor, and populated by the first generations of massive stars that forged heavy elements in their nuclear cores and scattered them across space when they died. 3. Atlas doesn't just come from another star system, it comes from another era entirely, when the universe itself was fundamentally different than today.